KBs. So where we ended Thursday is we ended up taking this down, saying the Ka equals H3O plus times A minus over HA. Did I mention the brackets mean concentration? Yeah. Okay, so your molarities would then get plugged in. And then I said that I wanted you to go through and solve for the KB. What'd you get for the KB?
HB plus, concentration of HB minus concentration of OH over concentration of E.
Okay. Why can we not refer to this one as the Ka anymore? Because aren't we doing the exact same thing that we did with the Ka? We're just multiplying the K by the concentration of water. Why would I not refer to this one as the Ka? Yeah, how do we know it's a base and not an acid? There's a what? The OH. Hydroxide versus H+. It's as simple as that. Okay? Sorry. Just the syllabus acknowledgement. So we could take this all the way down. We end up with the equilibrium constant. That then explains something about our reaction, and we could use that to apply or compare in a variety of different situations. When we're looking at those concentrations, they tend to be relatively small. So when we're looking at the K values, those K values also tend to be relatively small. Right? And by relative, we're looking at powers of 10, like 10 to the minus 6, 10 to the minus 7. So exponential values, really, really small. How many people are super happy and excited about exponential values? Yeah, usually most people aren't. Okay? So we end up inventing new ways to represent the equilibrium constant. Okay? But before we get to that, what we could do is take a look at water. And water does the same thing. We can dissociate into H plus and OH minus, just like we looked at our acids, just dissociating into the ions. And we could rearrange our expression, and we end up now with a new K. Because again, the concentration of water is huge, so it's not really changing when we dissociate. And we'd end up with a new K that looks like this. This K is referred to as the KW. W for water. Okay? When we change the temperature, we're going to end up changing the amount of dissociation, which means the H plus and the OH minus concentrations change. But they will always change when we're looking at our KW the same with respect to each other. So if I know the H plus, I can solve for the OH minus. So one of the questions that tends to show up on kind of MCAT kind of things would be, what is the pH of a solution at 50 degrees Celsius? Okay. Well, our KW, 10 to the minus 14, is typically what it's solved as, and you're usually told to memorize it and say a 152 class. Okay. Well, if it's 10 to the minus 14, we can then say the concentration of our H plus, would be equal to 10 to the minus 7, because we're saying x squared, take the square root of both sides. So the square root of 10 to the minus 14 is 10 to the minus 7. And we now have the concentration of our hydrogen ion. And they always throw in this pH. Why do they throw in the pH? This is an exponential value. Remember, you were all excited about exponential values? You're like, oh, those are totally easy. We're totally going to work with those for the rest of our lives. Okay. We didn't. Okay. We said those sucked. We wanted to change them into something else so that we don't have to deal with exponentials. What did we change them into? The pHs. Okay. So a logarithmic scale, which we haven't quite talked about, but it's on this slide. Okay. And we could say then that our pH is equal to the negative log of our concentration of H plus. So the pH for water, or neutral water, comes out to be 7. Okay, because the log is the anti of the power of 10. Okay. What happens when we change the temperature, though? Well, the amount of H plus and OH minus changes. Well, if the amount changes, is that going to change the pH? Yeah. Okay. So that's one of the kind of misconceptions that can come out of 152 is that if we change the temperature, we say, well, it's still water. The water concentration of H plus and OH minus are always equal to each other, so that means pH is always 7. No. That just means they're equal to each other. Whatever that value may be will change. So it's not always going to be 7. So to solve a question like, well, what is the pH at a different temperature? What do we need to know? To solve this, we need to know the kW. So they should give you the kW. And what they're asking you to do is do some kind of solve like this. Does that kind of make sense? Okay. So, as long as we're in water, okay, we can base everything around our kWs, and we can determine our amounts of acids and bases, which is kind of nice. And since we hate those exponents, that's where we bring in the p scale, which is just a log scale. So the pH is the negative log of the concentration of H+. Now you'll notice here I didn't write it as pH, I wrote it as px. Okay, why? Well, what if I want the pOH? What do I have to do? Negative log of concentration of the OH. What if I want the PE mic? Negative log of concentration of mic. It's as simple as that. Okay? So you see the P term pop up in a bunch of different places because what we're really trying to do is get rid of that exponential value. So we're looking at concentrations that end up being very, very small, and what we're trying to do is get them out of that exponential value and get it into something that makes a little bit more numerical sense that we can wrap our heads around. Okay? Which kind of gets us into our next situation. Okay, why do we care about this? Well, if we took a look at benzoic acid, or sodium benzoate on the left, what happens when I add H+? Okay, it becomes protonated. Now the structure, as we talked about Thursday, becomes less water soluble. Well, if we look at biological molecules, a lot of biological molecules are charged. So if we vary the concentration of our hydrogen ion, we can shuttle our structure between soluble and insoluble. And that can become very problematic for biological systems. Okay, which means what needs to happen to the concentration of H+ for most biological reactions?
Needs to increase.
It does not need to decrease either. It needs to stay constant. Okay? Whatever our system has established the pH needs to be, it needs to stay that pH. Any variance outside of that pH can cause a massive structural change, okay, or a solubility change. For most biological systems that we're concerned about, what pH do we tend to sit at?
So we said 4.
Roughly about 7 for those that are really nitpicking on details, which isn't me, but kind of eventually need to get there. 7.4. Okay? That is the pH for biological systems that we're primarily concerned about. Are there systems that are much lower pHs? Yeah, and we still have life there, but that life has designed itself around that pH. So that if we take them out of that pH and put them in a 7.4 buffer system, they very quickly die. Okay, so we have to maintain whatever pH our system was built around. Okay? So how can we control this? Because acids and bases are present everywhere. Right? They're so prevalent that if we think back to when we learned about chemistry, what was very typically the very first chemistry we learned about? Acids and bases. Why? They're everywhere. We have tons of definitions of acids and bases. It goes all the way back to the Arrhenius definition. Okay? He's really old and really, really dead. Okay? That definition continued to get refined throughout history. Why did we start with acids and bases? Those were the first things we really kind of discovered and isolated to any real extent. That's where chemistry kind of originated. Okay? So if it's so prevalent, is that going to potentially mess with the chances for biology? Yeah. Okay. If I took a human and dropped him in a vat of acid, that becomes a problem. Okay. So how does our natural biological system mitigate and prevent massive changes in pH? Because it's going to happen. We will be exposed to acid. we use buffers. Okay? So the whole point of a buffer is to react with our acid or base preferentially. That then either removes the acid, in which case there's no pH change, because the concentration of H plus doesn't change, or we add base and it removes the base. So the buffer acts as kind of an intermediary to stabilize the pH. Okay? Keep it relatively constant. Okay? So if we took a look, and since everybody seems to focus on the acids, let's keep our focus on the acids. Okay? What we're concerned about is our pH, how it changes, and we also want to know what our buffer is doing. Well, really, a buffer is just a fancy way of saying a balance of a base and an acid. What is A minus? Not a bad grade. What is A minus? You can spin it. What is HA? An acid, because it has a hydrogen that it can donate. So what is A minus? The conjugate base. What happens if I add acid? The acid will react with the base. What happens to the presence of the acid? Well, it disappears because it's reacted with the base. Okay? So in our K expression, we actually have a buffer. We have both an acid and a base. Okay? It's not formatted in a way that allows us to interpret it easily. Okay? And it also can be manipulated a little bit further to convert it into something that's easier for us to understand. Because remember, all of those values are exponentials. That value is an exponential. Exponentials suck. We don't want exponentials, so what could we do? What did we do to get rid of our exponentials before?
Change it to P.
Change it to our p scale. So what could I do to change it to a p scale? Take the negative log of everything. And if I take the negative log of both sides, those simplify down, and we end up with this fancy expression. The pH equals the pKa plus the log of A minus over HA, or the quantity A minus over HA. Okay? This is known as the Henderson-Hasselbalch equation, which if you took 152, you theoretically used, though I've seen some instructors that think it's too much of a cheat and students overuse it, and so they don't teach it. Okay? So we could use this to then see what happens to our pH. So if I take a buffer, so it's any species that has concentrations of acids and bases, I will know it's Ka, because Ka is a constant. And if I take the negative log of a constant, what do I end up with? A constant. Okay? So that value will be given for me, okay, or quickly solvable. Over here is now the concentration of my base relative to my acid. If I know those concentrations, I can then use that information to predict what the pH will be for that individual solution, okay, which is kind of useful. Okay? So what you would be expected to do is take a situation like this. If we had 100 milliliters of a 0.1 molar tris buffer, okay, so the buffers, which we'll talk about, usually have goofy names, really long, fancy, crazy names that we don't want to worry about. And they get abbreviated down into these stupid little acronyms like TRIS, okay, or HEPS, or I don't know why I can't think of others, but they get these silly little names. So if we take a buffer of tris that is 0.1 molar, okay, and it is established at a pH of 8.3, okay, and I'm telling you the pKa of it is 8.3, and we add 3 milliliters of 1 molar HCl, then what's the new pH? Okay. How many of you look at that and go, that's somewhat familiar? Okay. And I'm presuming everybody else is like, what the hell does that sentence even mean? Is that ballpark, right? Yeah. Guess what you're expected to do in a biochemistry class? Do that interpretation. For those of you that looked at that and it said somewhat familiar, what do you need to do to go through and solve this? Ice tables. Okay. Initial, change, equilibrium. Okay. We're looking at how these things all affect each other and change their concentrations. And it's an awesome, fun system of solving big, fancy equations, which is what you do primarily in 152. And since this is an upper division biochemistry class, of course I'm going to make you do this. But it's not upper division. So guess what? We won't worry about it. Were you going through and solving it back there?
I wrote it all down.
So we won't worry about it, so don't panic. Okay? If you want help trying to go through and set this up and solve it, we can do that, but we don't need to worry about it. Okay? We will look at more simple aspects of it. Okay? So this would be our ice charts. Yes, theoretically you're responsible for this, but we'll hold off on that. Okay? So what do I want you to be able to get out of this? Okay? Well, we need to have some interpretation of our pKa's. Okay? Remember, we're in biology, and our primary solvent in biology is water. So if we keep our focus on water and know its pKa, when I add a new species, I can compare back to water and come up with some balance or some understanding of it. So if I throw in, actually, let's look at the last one. What did we say the last one? The tris buffer had a pKa of what? Okay. What do you think? Is our tris acidic or basic? Why is it acidic? It's lower than that of water. Water is our neutral species, so if we have a pKa that's lower than it, which I know sounds weird, okay, that means it's more acidic. What if it's higher than it? It's not basic. It's less acidic, so we have to be careful with our pKa scale. It only tells us something about acidity. Okay? So if water is 15.7. If we're less than water, we're acidic. If we're higher than water, we're not as acidic. Okay? That does not necessarily mean basic. Okay? So we've got those kind of comparisons. The next thing we can kind of go through and do is pull some structural comparisons. And this is one of the things that kind of falls out of those calculations if you interpret the calculations as opposed to just cranking them out. Okay? If we're in an environment or in a solution, really what we're looking at is solving that Henderson-Hasselbalch equation, okay, which was pH equals pKa plus A minus over HA. And those are concentrations. I don't know if I had that in there or not. And officially that's the quantity. We can make some kind of structural evaluation. So if the pKa is larger than the pH, what does that mean? The pH defines whether we're acidic or basic. So if the pH is smaller than our pKa, what does that mean? Are we more acidic or less acidic? More acidic. Right? So we are in an acidic environment relative to our species. If we're in an acidic environment, which species would we expect to be present in a larger concentration? HA, because HA is our acid. Okay? That gives us some information, and we can now use that and evaluate that back to our structure. What if we're in a system where the pKa is lower than the pH? Okay, we're saying the pH is higher. We're now saying we're in a more basic environment than our molecule. Well, if we're in a more basic environment, what does that mean? Which species is present? A minus. Okay? Because it's all coming just from this. It's just those relationships. So if the pH is higher than the pKa, we're in a more basic environment. Which species should be present? The basic species or the acidic species? The basic species. What that then ties back to is what this is now referencing, the hydrogen being on the structure or off the structure. Right? And that can become challenging when we look at our structures because depending on the structure we're looking at, it may be drawn with the hydrogen on, it may be drawn with the hydrogen off. You're responsible for recognizing which state it's in. Okay? Which is challenging, but we'll see that when it pops up, primarily with our amino acids. Okay? So the big part that I really want to get out of this is an interpretation of graphs. And everybody hates interpreting graphs, but it's probably the most important thing for any kind of test. Okay? How do you interpret the information given? So what we've got here is a titration curve. Okay? Notice when we interpret any graph, we'll look at our axes to try and pull some information off of it. Okay? On our y-axis, we're measuring the pH. Where does my curve start? Okay, 1.1, I'm hearing 2. All of that, I would say, is too quantified. Acidic. Okay. If you start bringing the numbers in, you're now adding a layer of interpretation on it. Make it as blanket statement as possible. We are starting acidic. Where do we end? Basic, because our pH is higher than 7. Okay. What's happening on our x-axis? Milliliters of question mark. What a twit. I'm titrating something in. An amount of something is being added to cause the change shown on the y-axis. What is that something being added? A basic thing. Okay. When we're looking at our titration curves, we don't actually want to add a buffer, because that actually makes things more complicated than we need to. When we're doing the titration, what we're doing is adding usually a strong acid or base to see how that strong acid or base affects the buffer. So what we're seeing here as the curve is our buffer system. Okay? And what happens as we add a species to it. The species we're adding to it must be the base because, well, we started acidic and we ended basic. The only way I go from acidic to basic is adding base. Okay. The standard base that almost always gets added is NaOH, or sodium hydroxide. Okay, but we're just adding some kind of base. Okay. So we now want to start to layer some more information in here. Do we know more about this species? Technically, yes. Okay, but what we're trying to do is layer that in slowly. Okay. If I'm starting with an acid, let's define it. How would I know? What would its structure look like if it was an acid? H plus is the result of it having acted as an acid. That's not the acid itself. It's protonated. So I know there's a hydrogen present, and that hydrogen is connected to something. Okay? Acid happens to begin with A. There we go. Okay. What happens as I add a little bit of base? So if I'm starting here, what happens when I add just a box of base? The pH increases. Should I expect the pH to go up? Why? I added base. How much did it go up? Not a lot. Why did it not go up a lot? What did the base react with? The acid. The instant the base reacts with the acid, do we have any more base? No, which means no change in the pH. Okay? So we're adding our OH minus. The result is I would end up with A minus and H2O. For those of you writing as big as I am, you might hold off and write a little smaller. Okay. What happens as I add a second box of OH? Okay. A little bit more increase. What happened? The pH stayed relatively constant. Why did the pH stay relatively constant? There's more acid present. That acid reacted with the OH minus. Now no effect to the pH, because the result is no H plus or OH minus. Okay, so no change in the pH. Okay. What happens as I add that third box? Continues. Fourth, fifth, sixth. I'm going to guess that's somewhere near 10. What happens when I get near that 9, 9.5 range? I see a big jump in the pH. Why would the pH all of a sudden spike? Good. Keep going with it.
Threshold.
What threshold? It's actually not an equilibrium. Why did the pH not go up over here?
Because it was turned into water.
Yeah. This species was present to kill it. Why is the pH going up here?
Because there's not enough proteins.
There's no more of this. That's why it's spiking. There's no more of the acid species. If the HA is no longer present, what's going to happen? Well, now the hydroxide concentration immediately goes up based off of just the added base, and my pH should spike like crazy. Okay? What we just walked through now allows us to elaborate some more information here. At that initial point, right where we wrote acidic, what do I know is present? HA. Okay. At that next point, what do I know is there? Okay, and this one gets tricky. Okay, I'm nailing this down. So let's try the first part. Is there any HA? Why did the pH spike? Because there's no HA. If there's HA, what happens when I add the hydroxide? The pH doesn't change. Is the pH changing here? Is there any HA? No. There's no HA here. So what is there at that point? Okay, we could say no HA. We could say OH. It's a little bit of a questionable one to draw in there, but we can say that. Okay, that's why it's going up. So we have a higher concentration of OH minus. Okay. We could say water, but water was in the whole thing. What happened to, and you may have just said it, what happened to the HA? It became A minus. It didn't just disappear. What I actually have present there is now A minus. Okay. What other information can I pull from this? Well, we're being told the pH is 4.01. Okay, great. Okay. Could we use this expression, the Henderson-Hasselbalch expression? Okay, I have no HA, which means its concentration is 0. What is a number divided by 0? Try and enter it into your calculator. Depending on your calculator, you'll get a variety of different answers. Usually it freaks the system out. Okay? If we do a number divided by an infinitesimally small number, we end up with an infinitely large number. Okay? And again, depending on how your calculator permutates it, it can either cause it to error, it could say it's infinite, it could say it's 0. It pretty much destroys the limit of how we calculate because it is approaching an infinite number, and we don't have a way of representing that on the calculator. Right? That shuts that whole equation down. Okay? We now have an error within the calculator. That equation becomes useless. Okay, well, it would be really nice if I could find out, using this titration curve, some information about HA. Okay? So one of the things that we said we needed to determine our pH was the pKa. Well, that has to be calculated somehow. Can it be calculated using our titration curve? And 152 people should be able to tell me emphatically. Some of you I know took 152. Yes, you can figure it out. So now the question is how and where? We just said we can't figure it out here because this equation shuts down. For this equation to be valid, what needs to happen? I have to have a concentration of both those species. So I could pick any arbitrary point and determine what those concentrations are. That means trying to figure out the concentrations at any one of those points, and that can be a bit tedious of a calculation to go through and do. There's a faster way. What is that faster way? And maybe this will help. That point was referred to as the equivalence point. The amount of base I added was equal to the amount of acid that was present. That trigger any nightmares, like flashbacks? Seeing some heads shaking yes. What should that be triggering? Anybody pick that one up? 1/1, what are you referring to?
It's like the same.
You're saying when those concentrations are identical, right? What happens? Those become 1. Log of 1 is 0. If that's 0, pH equals my pKa. Awesome. When do those concentrations equal each other? And it's not necessarily 1/1, but the concentrations will be equal. At the half, see, half, right? There. Half equivalence. Oh, I really deleted everything. Can I go back? What's that button? No, that didn't do it. Oh, man. Okay, well, we said this was our equivalence point. What's the half equivalence?
Slope is closest to horizontal.
True, but there's an easier way.
Just halfway in between.
Okay. If I'm 6'4", half of 6'4" isn't roughly in my middle. It's exactly half. If this is the equivalence, I need to go to exactly halfway to the equivalence point. How did I get to the equivalence point? Adding base. How do I get to the half equivalence? Add exactly half. Okay, which I think is that one. If I counted the lines roughly right. That is now defined as my half equivalence. At the half equivalence, what happens? Well, Janelle suggested A minus equals concentration of HA. Which also then means the pH is equal to the pKa. And I now know for this particular acidic species that its pKa happens to be, these all unit 1, 2, 3, 4, 5, 6, yeah. The pKa is 2. That's pretty awesome. I've got some quantifiable numerical information off of a curve that really I ignored all the quantifiable information on. That's pretty phenomenal. Right? That's the idea behind a graph or a picture. That's what we're supposed to do with them. If it doesn't give us that information, it's a horrible picture. Okay? So, question? Just thinking about it? Okay. Is that all the information that's on this curve? So it just goes whoop and it stops. What happens as we add more base? The same thing. What happened as we added more base? The pH changed suddenly and then all of a sudden leveled out. Why did it level out? Why was it level here? HA was present. An acid was present to neutralize the base. Why is it level here? An acid is present to neutralize the base. Can it be HA? No, because once we hit this equivalence, what happened to HA? It's gone. New acid. So I had 2 acids present in this, sort of, kind of, but that adds and makes things more difficult. Okay. What I started with was actually not HA. What did I start with? H2A. So in the first part of that curve, and sorry, I'll color code that. In that first part of that curve, when I added the OH minus, what happened? I got rid of a hydrogen and I became HA minus. What is special about HA minus? It still has a hydrogen, which means it can still act as an acid. So when I run that first reaction, yes, I neutralize all of the hydroxide or H+, but then HA can go through and react with more OH minus to produce A minus 2, because we lost a second hydrogen, plus H2O. So be careful because you're doing the dissociation of this versus the reaction of this. We're reacting it with hydroxide. Okay, we're still adding base. Okay. So now what happens? I add base, and I no longer have H2A, but I have HA minus. So at that equivalence point, the red equivalence point, I now no longer have no H2A, but I have everything as HA minus. What happens as I add base? Well, the pH spikes initially and then levels, okay, when I've kind of finished out the equilibrium of the previous system. Okay. What happens to HA minus as I add more base? It reacts with the base. pH doesn't change. It stays relatively flat. Okay, until what point? Until I reach another point where I've added enough base to react all of the HA minus. And I would reach yet another point. What is that other point? It's the equivalence point. Okay. Could this become confusing? We have now two equivalence points. So we might separate this out as the first equivalence and the second equivalence. Okay. Now that we're at the second equivalence, what do we know to be true? There's now no HA minus. Officially, there's also no H2A, but we ran out of that. So there's no HA minus. What else is present there? I have A minus 2. Everything has become now A minus 2. Okay. Remember, we want to be able to pull quantifiable data off of this. Where can we get that quantifiable data? At our half equivalence. So if I look at the volume, halfway puts me here. Is that the half equivalence? Half equivalence for the reaction that was run, which is now just between those two lines, which means our half equivalence sits right in the middle. Okay, for the reaction that was running. At that half equivalence, what do I know to be true? The pH equals the pKa. Well, what happened at the first equivalence? pH equals the pKa. Well, which is it? Is it the red pH or the purple pH? Both-ish. So we should be a little bit more careful. This isn't pKa and pKa. This is pKa 1, because it was the first one we encountered. And the other one is pKa 2. Why did it level out again? We've reached the saturation limit for water for base ions, for hydroxide ions. So it's leveling out again because it can't get any more basic. Okay? So it's not buffering. So that now brings in our question of where do we know we're buffering? Well, the whole point of buffering was that what happened to the pH? No change. So where do I have the capability for a buffer? I have a section probably more like in here. As a buffer, where else? Roughly the same area in the one above. Those are now my buffer zones. Within those zones, where's the best place to have a buffer? Sorry. At the half equivalence. Why at the half equivalence? What happens when I add acid? It gets slightly more acidic, but not much. What happens when I add base? Slightly more basic, but not much. What if I picked right at that tail end? For those potentially watching this at home, what if I picked this point as my buffer? What happens when I add acid? It starts to drop very, very quickly. So my ideal buffer range is going to be as close to the center point as possible. Okay. Any distance off of that means I start to become less of a good buffer because I only have a small range in which I can buffer. Kind of makes sense? We good with that? Kind of a mess of things to label on that, but that's what we should be getting out of those titration curves. Okay. For those of you going, oh my gosh, that's a bit crazy, guess what? Take a look at exam 1. You have a titration curve. Okay? So if you have questions, it's fine. We can go through it. Do we need to do it all over again? Office hours are awesome. Okay. So, buffer selection and preparation. We've got a bunch of names of buffers. We've got their respective pKa's, and then I've labeled them A, B, C, D, E, F. And I forget why I called them L and P. I don't know. Which buffer should we use to achieve each of those pHs? So pH is 1, pH 4, pH 6, pH 7, pH 8. Okay. So see what you can come up with. See if you can list an appropriate buffer. All you need to do is say A, B, C, D, E, or F. See what you got. Have you got questions on this curve? Okay, our best buffer was at the half equivalence. So we're centered in there, and we're centered here, right? What is true at the half equivalence? pH equals the pKa. Okay. So if I want a pH of about 6, what I'm going to do is set up the concentrations of my species. Remember we had H2A going to HA minus, going to A minus 2. Which species should be present to get me a pH of 6?
HA.
Say that again?
HA minus.
HA minus, is that it? HA minus is a good acid. What happens when I add acid? pH is going to drop because HA minus can't, as an acid, can't react with an acid. What else needs to be present? Conjugate base. Okay. So if I want a pH of 6, remember this was the transition from HA minus, yes, transitioning to A minus 2. To get exactly halfway in between, what's present? HA minus and A minus 2. Okay. So I'm going to target based off of that system. My pH needs to be as darn close as possible to the pKa. That's going to be the ideal system. So what happens when we look at these? If I want a pH of 1, should I be picking tris? Its pKa is at 8.3. Its ideal buffer spot is at 8.3. To get it to a pH of 1, what do I have to do? Add a bunch of acid. I add so much acid that when we look at tris, what's present? Right, and I know we're going to pretend with our structures. We've got tris back and forth with, and because we've always been starting with the acid on the left, let's continue that, with tris H. Okay. At 8.3, I've got the perfect balance between these. To get it to a pH of 1, what do I have to add? Bunch of acid. So much acid that what happens to the tris? It goes away, and all I have now is tris H. To be a buffer, what happens when I add acid? pH stays the same. The reason the pH stays the same is because there's a conjugate base present. To get down to a pH of 1, do I have the conjugate base? No. So tris is an awful buffer to use because I can't achieve a balance of both those species. Which buffer would work best? The phosphoric acid. Okay. Gets me as close as I possibly can. Okay. How about a pH of 4? What do you guys think? I think it's phosphoric acid or potentially carbonic acid because it sits pretty much right in between them. What a mean question. How about 6? Probably just our carbonic acid. 7? C or D. 8? Just our tris with our F. Okay. We're just trying to pick a buffer that's as close as possible. How do I get the tris buffer to be exactly at a pH of 8? What do I have to do? I'll have to add acid. Because if I have just the tris buffer going in at 8.3, it needs to get down to an 8. The way it gets to an 8 is by adding strong acid. Does that take it out of the ideal buffer range? Yes. But what I'm hoping is it doesn't take me so far out that I can still buffer reasonably well there. Make sense? Okay. How do we, well, let's see what the, because I forgot. We talked about this already. This is in a slightly different format. It's the relationship between our pH and our pKa and deciding HA being our protonated state, pH versus pKa being our deprotonated state. Okay, we have to be able to recognize those structures and decide which way we balance. Okay, kind of makes sense? So one of our big decisions behind choosing a buffer is what pH we need to match, which then means what pKa. That is hugely important. It's probably one of the primary concerns. Okay. Which then leaves us with this big open slide. Let's see, did I just stepwise it? Okay, there we go. There's number 1. We just spent 20 minutes, hour, something like that, figuring out bullet number 1. To get a good buffer, we need a suitable pKa. What else should we consider? Because I think we've got at least another hour left, right? And I think there's 6 bullets, so only 6 more hours left of class. Just kidding. What else might we want to be concerned about within our buffer? In theory, it was in the textbook that you read. Maybe. Maybe not. It's okay. Some of you could cheat and look at the slide, which looks like Terry might be doing. You got it. You can shout one out.
So is this relative to how far along that horizontal curve
Okay.
you are?
For which? The pKa?
On the titration curve. If you get
Yes. The suitable pKa is deciding where you are along that curve. Yes.
Oh, that one is okay.
Okay. The next one, no interference with the process being monitored. Okay. The buffer is supposed to balance our hydrogen ion concentration. Okay. Most biological molecules, are they responsive to hydrogen ion? Yes. So most biological molecules can act as buffers, and by definition do. If I want to study ATP synthase, should I use ATP synthase as the buffer? Okay. I'm now trying to study an object that is also the buffer. The whole point of the buffer is that what happens? Nothing. Nothing happens. That's the ideal buffer, that our pH does not change. If I now want to study ATP synthase that is now also acting as the buffer, well, the buffer says nothing happens. And when I study something, okay, if you think about what things you study, do you study paint drying? Why not? Why is it boring? Nothing happens. Okay? So what I'm looking for a buffer is to make sure that it is not messing with or interacting with the system being studied. Okay, so I kind of cheated and gave you a different one. Okay. The buffer cannot interact with the process being monitored. Okay. So what if they talked to each other? Well, the whole point of the buffer is that it has no interaction. It does nothing except to make sure nothing happens to the pH. If the buffer also talks to the species I'm studying, I'm going to have a communication issue. That's going to mess with my observations. Suitable ionic strength. And this kind of goes to where I think you were referencing, Terry. What does that mean? Well, let's take a look at a buffer. HA needs to go to what? A minus. And for it to be a suitable buffer, what do I have to have present? hint, the answer is actually on there. To be a suitable buffer, what do I need to have? HA and A minus. If I don't have both of those, do I have a buffer? No. The whole point of these is if I add acid, what happens? H plus reacts with the A minus, no change in the pH because the H plus is gone. If I add a base, OH minus, what happens? Reacts with the HA, no change in the pH. Okay? So our buffer means we have both of those present. That's getting back to our suitable pKa. What are we saying when we look at ionic strength? If someone is strong, what does that mean to you? You can even look at emotional strength versus physical strength, either one. If someone's strong, what does that mean to you? Nothing? You're like, yeah, strong people, whatever. You don't like strong people? What does it mean if you're weak? What's that? Can't do things. Okay, so if we're looking at physical strength, they can't lift things. Okay, or they can lift only small things. Okay, so if I had a weak ionic strength, what does that mean? It can't deal with a lot of acid or base. It can only deal with a small amount. So the whole point again is that I have some of both of those. So let's pick a buffer where we put some of those in. Let's say I have one molecule of each. Is this going to be a buffer? Careful. Is it going to be a buffer? Yes. Is it going to be a good buffer? No. Why no? I add one molecule of hydroxide and what happens? This disappears and becomes zero. Do I have a buffer anymore? No. Okay. The ionic strength is how concentrated those species are. If they're too dilute, when I add acid or base, I no longer have a buffer. So I need a sizable amount of those. Say 1,000 could get a little bit better of each. And we know 1,000 is probably still not very good because chemistry works at what scale? Begins with an M. Mole scale, which is 10 to the 23rd. Okay, well, 1,000 is 10 to the 3rd. I'm off by 20 factors of 10. It's just a little bit off, right? Okay. So what we're looking for our ionic strength is something that has a sufficient amount of both to act as a buffer. They have to be present. Okay. And I think we have the exception to that one shown on a later one, so I won't talk about it yet. Solubility issues. Yep, we do. Okay. We take water, we add salt to it. What happens to the salt? Dissociates. What would we physically see? Dissolves. Just trying to make it simple. Okay. You keep adding salt, what happens? Dissolves. You keep adding salt. It saturates. We keep adding salt, and what happens? It doesn't dissolve. What happens if we try and dissolve something else in it? It won't dissolve. What we've reached is the saturation limit for water. Most liquids, when we try and dissolve things in them, have a saturation limit. Okay? And at that point, we can't physically dissolve more in it. So when we're talking about solubility issues, I want a sufficient ionic strength. Okay? So let's say instead of a mole, I do 50 billion moles. It's a bit excessive, but you get the idea. Would I be able to dissolve any of the thing I'm trying to study in? No. The solvent is now so overwhelmed with the buffer that I can't put anything else into it. If I can't put anything else in, I can't do a study. Okay? That's what we're talking about when we talk about solubility issues. Okay? We've reached a saturation limit for the solvent. So we have kind of a sweet spot that we're aiming for. Numerically not important. What you're recognizing is that there is one. Kind of makes sense? Okay. Last one, non-biological nature of the buffer. Why might this be important? As a sort of hint, it's actually already on there. The non-biological nature of the buffer is effectively the same thing as number 2. no interference with the process being monitored. Okay. When we move into the third unit, the very first slide I've got, and I'll try and remember to delete it from the PowerPoint that I post to you guys. So PowerPoint's usually maybe a couple meg in size. That PowerPoint with that image jumps up to like 50 meg, 60 meg, because it is this massive spiderweb network of all of the metabolic pathways in biochemistry. Right. And when you look at it, you can pick any individual point, and that game was at 7 degrees of separation. You can tie it to pretty much any other point in metabolism. Which means if we take a single molecule out, try and study it in biochemistry, if we pick a buffer that is biological, more than likely, it will interfere with the process being monitored. Okay? So most of the buffer systems we see are non-biological. That's where you get tris and heps and all those weird names that we saw. Okay? We're trying to pick buffers that don't affect the biological system. Because if our buffer affects it, we're not observing just the chemistry, we're observing the chemistry and some secondary chemistry. It's too hard to predict what's actually happening. Make sense? Okay, excited about buffers yet? I was going to talk about, well, we can kind of talk about this. To get into organic chemistry, because what we're looking at with buffers is acid and base strength. So based on your understanding of organic chemistry, which of these two buffers would best buffer at a pH of 10? Yeah, and everybody's probably like, what? You can't do that. It's actually a lot harder than I intended to be. So this is one of the things with understanding the protonation states. So when we look at those structures, what are we trying to identify? The functional groups, and in particular, which functional groups are we concerned about? The acid and base functional groups. And so when we look at these, hopefully, you might recognize that guy as being the same in both. Okay? And as soon as we say same, that's going to be a problem because one of them is supposed to be better than the other. Okay? So if they're the same, that's probably not good. That functional group at the end should look very kind of familiar to you. Should look kind of like, yeah, sulfuric acid. And what do you know about sulfuric acid? It's a strong acid. Okay? Which means when I add these buffers into solution, what do they instantly do? They ditch that hydrogen. And that hydrogen ends up being completely irrelevant to this. Why was it actually drawn on there? Because one of the kind of bad habits of both organic chemists and biochemists is we tend to draw things in their neutral states, even though the neutral state probably isn't the most valid. Okay? Which means neither of those two are going to be able to balance at a pH of 10, because you said it's a strong acid, and if it's a strong acid, will it accept a hydrogen? No. So we can never form the acidic form. We'd have the conjugate base at that point, but we never have the acidic form. And to get a buffer, we have to have both. So it can't be that position. So, what do we have next? We have the nitrogen. And what do we know about the nitrogen? It is basic because it has an implied lone pair of electrons which can be shared with a hydrogen. Okay. So both of these buffers are being drawn in which state? I know it's kind of a vague question. Let's see what you can come up with first. Acid state or base state? How it's drawn. Well, how it's drawn now. Yeah. Is this drawn in the acid state or the base state? It's the base state. Okay. And our focus is on that nitrogen. Okay. Why would it be on the nitrogen in the second structure and not the oxygen? You're close. I mean, you're right. Oxygen doesn't want to share its electrons, What we're looking at is the lone pair on our nitrogen versus our oxygen and saying which of those is more likely to share with hydrogen. Why would the nitrogen share with hydrogen preferential to the oxygen? Electronegativity. Okay? Nitrogen is less electronegative than oxygen, meaning it is more willing to share its electrons. The oxygen is kind of a misnomer here, just there to kind of mess with the overall chemistry in this. So what we're comparing is those two nitrogens and their abilities to pick up a hydrogen, okay, and deciding would they become acidic or not. Okay, which gets very, very challenging. So what we'll do is draw out, there's our acidic state. Versus our acidic state. And we want to try and come up with some comparisons on how and why one might be better than the other. Okay? It is a lot more complex than I had intended, but let's see what differences you guys pick out. And yes, I simplified the one on the right. What differences do you see?
The connections to the nitrogen.
Okay.
Carbons and
Known as, not really sterics. The number of carbons attached, primary, secondary, tertiary. So we have a secondary, tertiary issue. What else do we have going on?
You said no sterics?
Yeah, no sterics.
Is that nitrogen more stable?
It's in a ring structure. And from probably chapter 4 in everybody's organic chemistry book, what would we be looking at? Chairs. Everybody's favorite. And when we look at the chairs, by adding that hydrogen there, okay, because this big old group is large, the large group goes into which position on our chair? The equatorial, which means the hydrogen is necessarily going to go into the axial. What's the issue with the axial? Flagpole interaction, steric strain. That molecule now becomes inherently unstable. If it's unstable, what does that mean it's trying to do? Become stable by doing what? Getting rid of the hydrogen, which suggests that hydrogen is acidic. To be at a pH of 10, should we be acidic or basic? Basic. What does that mean? The one on the left is probably the better buffer. Right? I want to talk about that because that's getting at organic chemistry, looking at all that structural and fun stuff. As a biochemist, what would you look at? Okay. Probably what you would look at has nothing to do with those structures. You would probably be looking at the letters for the name because you don't even know how to name them appropriately. And you would look up the pKa's associated with them. And you say, oh, that's it. And then say, well, there's no organic chemistry in biochem. It's there. We just choose to ignore it. Except me. Sorry. Fun stuff. So, blood buffering. Here's another fun one. Some biochem. Okay. This process goes on in your blood every day. Conversion of CO2 into bicarbonate. Okay, it's one of the things that contributes to the stability of your blood, making sure that you don't die due to pH changes. Okay. There's an enzyme that helps us out. It's known as carbonic anhydrase. Okay. What happens to the pH in the lungs? What would you expect? What is happening in your lungs? You are expelling CO2. So which side of the equation would we expect to be favored? If we're on the right side, where's the CO2 going? Into HCO3, which is aqueous, which means it's going into bloodstream. Do we want CO2 going into our bloodstream? In the lungs? No, we want it leaving. So more than likely what's happening, the left side is favored, which means what would we expect to happen to the pH? So here's where we have H+, but what's happening to the H+? It's disappearing. So I'm losing H+. So am I acidic or basic? Basic, which would mean the pH is above 7 or higher. It should be basic. Okay? What would I expect in the muscles? Okay. We're producing CO2, and we want that CO2 to go the other direction, so we might expect acidic. Okay? Is that necessarily the way it works? For those of you in the biology sides of it, you remember how your pH changes? Okay. I've been corrected and told that's not the way it works. Okay. Is there something else involved in blood buffering? Yes. Okay. It's called hemoglobin. Okay. It has a secondary effect in blood buffering as well, which contributes to pH contributions. So it's not just CO2 and carbonic acid or bicarbonate. Okay, but what we're doing is looking at what we know to be happening in those cases and saying how our equation shifts. Kind of neat. Okay. In an experiment to evaluate carbonic anhydrase. So now I want to study carbonic anhydrase. Okay. Would carbonic acid be a good choice for the buffer? Okay. And for those of you that don't know your nomenclature very well, that's okay. You just got to let me know. Carbonic acid is H2CO3. What would H2CO3 likely act as? HA or A minus? HA, so it would turn into HCO3 minus. So here's our HA, here's our A minus. Would this be a good buffer system to use? Why not? What does carbonic anhydrase do? It does this reaction. HCO3 as a buffer and as a reactant or product, depending on your perspective, in the reaction of the enzyme you're studying. That contradicts one of our rules. Okay? Our buffer cannot biologically interfere. We need to make sure it's separate from it. And that's why we invent all those fake bases, aren't fake bases, fake buffers, whoops, that we saw up on that slide. Okay? Those are biologically not relevant. Kind of make sense? Excited to move on? Let's look at some amino acids. Because for those of you being like, all that, thank God, that acid-base titration stuff, I don't have to worry about it. It comes back. Sorry. Okay, amino acids. What does the name suggest? There's an amine and an acid. If we looked at a polypeptide or a protein, we're linking multiple amino acids with each other. Okay, and when we look at an amino acid, okay, it could be listed as the amine on the left and the acid on the right, or couldn't I have just as easily picked the structure up and flipped it over? I would have had acid on the left, amine on the right. Okay. Which way should I be looking at it? This way. The amine is always on the left, the acid is always on the right. Okay, that is the default way to look at an acid. If you ever wonder, just say amino acid. The name gives it to you. Okay? So when we're looking at these, your amino acid is the monomer. It's a single unit. The protein is your polymer. We're linking multiple of these together. Okay? And your N terminal is always listed first. The amine, which we just talked about, the nitrogen has what? A lone pair of electrons, which means the nitrogen can act as a base. Because it can act as a base, we now have acid-base characteristics that we should identify and potentially look at pKa's. This gets nasty with amines. pKa of 9, does that mean acidic or basic? It's not being compared to the pH, it's being compared to the pKa of water. Okay, that is more acidic than water, because water is a 15.7. Okay. Which hydrogen do I remove? What is the acidic hydrogen in this structure? Yes, that is an intentionally mean, tricky question. Nope, not really, not to any strong extent. Which acidic hydrogen on the amine? represents the pKa of 9? It's not there. This is drawn in the deprotonated state. The protonated state that corresponds to the pKa of 9 means there's another hydrogen present. Okay. Amines are very tricky for that reason. We're now looking at that hydrogen corresponding to the pKa of 9. Anybody know the pKa of the other hydrogens? 36. Is that more acidic or less acidic than water? Okay, less acidic than water. So given the choice, because I'm in a water environment, where would I remove the hydrogen from first? That purple hydrogen or from water? Water. Okay. Will I ever reach an environment that is basic enough to remove that hydrogen? In a biological system, absolutely not, because I need to center at that pH of 7. Okay? So those hydrogens, the NH2, those hydrogens never get touched. The extra hydrogen in the protonated state, the NH3, that is our acidic hydrogen. We have to be very careful with that. Okay? When we move to the acid portion, that becomes a little bit easier to deal with, because the acid portion is drawn in the acidic state, typically. Its pKa is about 2. Do you need to know the pKa of the acid and the amine? Yes. Okay. Those are very important numbers to have memorized. You need to know them. Largely because we have 20 amino acids, and the pKa for the amine and the acid in each of those 20 amino acids varies by 0.2 pKa units. They're almost identical. So if you just memorize them outright as pretty much 9 and 2, you're golden for the primary functionalities. Now all you'd have to remember would be your side groups. Okay? When we go through and build a peptide, what we end up doing is linking multiple amino acids. So when we look at this, we have an amino acid 1, 2, 3, 4. Okay? And when we draw that out, notice the amine starts on the left because that is our default. Our acid starts on the far, or ends on the far right. Okay? Which brings up the next point. The pKa of 9 and the pKa of 2. Do I care about the acidity of the amine and the acid in most polypeptides? It's a kind of harder question. How many amine acids or amines do I need to worry about in the polypeptide shown? 1. How many amino acids are there? 4. Why do I not care about the other 3? They're buried in the backbone of the polypeptide. That nitrogen, while it still has a lone pair of electrons, is no longer basic because everybody's favorite 9-letter word? Resonance. Those lone pairs are not accessible for acid-base character because they're stabilizing the backbone. Okay? So we only have to care about the end and the the end and the beginning, and then whatever our side chains are, which we'll talk about on Thursday.